So transmission we decided to do is 42LE. It's out of a 2002 300M. But it would work in any LH car, Concord, LHS, 300M, Intrepid. Basically, it's a very unique setup compared to most front-wheel drive cars. It's a longitudinally mounted transmission, so the engine is sitting like any normal rear-wheel drive would sit, except it's front-wheel drive. So two shafts come out on each side of the transmission to the wheels instead of having it sideways or laterally mounted, as most front-wheel drives in America are. The reason Chrysler decided to use the longitudinally mounted engine and transmission is because they wanted space savings. They had a cab forward design when they designed the Intrepid, so they wanted a short hood and a low stance in the front, which ultimately gives you better fuel mileage, a better looking car, and basically with the cab forward design, it keeps all the wheels closer to the corners. Basically more of a design standpoint than anything else. Okay, so here's the transmission case. This is an empty case. All the hard parts have been organized on the bench to where it would be this way inside of the transmission. So you have your torque converter at the front, and then this is the transmission pump. This is the stub shaft coming from the differential. It goes behind the torque converter, which is very abnormal compared to any normal transmission. From the transmission pump, we go to the input clutch assembly, which is connected to the input shaft and both the planetaries. This is where all the magic happens when it comes to switching gears and different ratios and everything inside of the transmission. This is where all that happens. And from the output shaft, you have this gear connected, which transfers all the force through the chain to the transfer shaft gear. Transfer shaft gear is connected to the pinion shaft, which, as you can see, it's just like any normal axle. And the transfer shaft, or the transfer gear, would be connected right here. The pinion shaft, as any differential, is connected to the ring gear, which is just like any open differential, and it has a stub shaft here and a stub shaft that goes inside of here, and that's what's connected to the CV shafts, which in turn turn the wheels. Mechanical power flow on a 42LE starts at the flywheel, which is bolted to the front of the torque converter. The torque converter has three main parts internal to it: the turbine, the stator, and the impeller. The impeller is at the front of the torque converter, and it's basically spinning at engine RPM. And the stator is a stationary member of the torque converter that is held stationary by the reaction shaft, which is internal to the pump on the LH cars. And basically the stator's job is to redirect the fluid from the impeller to spin the turbine. The turbine spins the input shaft and in turn spins all of these. Okay, so I pulled up an image of the 42LE written on a piece of paper with numbers pointing to each part internal to the 42LE. Starting at 18, the torque converter, that's where we started on the overview of the mechanical power flow, and then we went through the torque converter and the input shaft, the clutch assembly. So what is inside the input shaft clutch assembly is 13, 12, 11, 10, and 9. And inside of the input shaft clutch assembly is the two planetary sets, along with 13, which is the underdrive clutch pack, 12, which is the overdrive clutch pack, 11, which is a reverse clutch pack, 10, which is a 2/4 clutch pack, and 9 is the low reverse clutch pack. So for the 42LE's mechanical power flow, we'll start with first gear. As you can see on the application chart, the underdrive clutch is applied along with the low reverse clutch for first gear. This gives you a 2.84 to 1 ratio from the input shaft to the output shaft. So now I'll demonstrate for you what happens when the underdrive and low reverse clutch are held. As you can see, I'm holding the low reverse clutch while I'm spinning the underdrive, and you can see there's one time around, twice around, and then you'll see it'll go a little less than a full rotation for the third time, and that gives you your 2.84 to 1 reduction from the input shaft to the output shaft. It also can be noted that the Low reverse is holding the outside of the planetary, while the driven clutch is the underdrive clutch. For second gear, the two clutches that are applied are the underdrive clutch, which is the driven clutch, and the 2/4 clutch, which is the holding clutch. For second gear, the reduction from the input shaft to the output shaft is 1.57 to 1. It's a little less than first gear, obviously, but it's definitely getting up there in the ratios. Now I'll demonstrate this by holding the 2/4 clutch and spinning the underdrive clutch as the driven. And as you can see, there is less of a reduction. There's one time around. And as we come around the second time, you'll see right before a full rotation, it is already at the point where it needs to be for 1.57 to 1 ratio. Third gear in this transmission, it is a 1-to-1 ratio, which basically means that two driven clutches are held so that everything moves as one. So in this case, it is the underdrive and the overdrive clutches that are held, and this will cause the input shaft and the output shaft to turn at the exact same rotation. So now I'll demonstrate the 1-to-1 gear ratio for third gear, and as you can see, I'm holding underdrive and overdrive, and it is spinning at the same speed. For overdrive, there are also two clutches that are held, the overdrive clutch and the 2/4 clutch. Overdrive in this case is the driven clutch, and the 2/4 is the holding clutch. The ratio in overdrive is 2.21 to 1, so the input shaft will actually be spinning slower than the output shaft is, and this is obviously for highway speed sort of driving. Demonstrate this for you on the bench. As you can see, I'll be holding the overdrive and the 2/4 clutch, and you'll see that I won't even get a full rotation out of the input before the output gear is back centered. So this is fourth gear or the 42 LE. So for reverse, there are also two clutches holding. There is the reverse clutch and the low reverse clutch. In this case, the reverse clutch is driven and the low reverse clutch is holding. In reverse, the ratio is 2.21 to 1, and obviously, since it is reversed, the input will be spinning a different way than the output. Demonstrate for you reverse on the bench. So there is the reverse and the low reverse clutch. As you can see, I'll be spinning the reverse clutch and holding the low reverse, and as it spins, it's spinning in the opposite direction from the input to the output, and that gives you the reduction in reverse.
Today we're going to take apart this 42 LE input clutch assembly. First thing we're going to do is remove the planetary gear set, sun gear, planets, and the ring. That gets removed. That would normally not be on this, it's just on here for the demonstration purpose. So this is the input shell. The first thing you're going to do is remove the top snap ring. This is called the reaction plate snap ring, as this is the top reaction plate for the input. This is the reaction plate for the reverse clutch and is used to hold the clutch in place. It's got to be pried out of place. And once it's removed, you can see this is the wear surface where the clutch would be riding on, and it's out of the way now. So now the reverse clutch can be removed. And there are two frictions and only one steel. That's all it needs for a reverse. Holds in place and stays right there. Next is the overdrive reverse pressure plate. To remove that, there is one snap ring at the top. That has to be removed. Now that that's out of the way, the overdrive reaction plate can be removed. Now this is a dual purpose. It serves as the stationary member for the reverse and also the reaction plate for the overdrive reverse. Okay. So next, now we're looking down in, there are the overdrive clutches. Now they can be removed right now simply by removing this, which holds them all in. There are 3 steels and 4 frictions there. That's your overdrive clutch. Now that that's all the way out, there's another snap ring here. This is a waved snap ring. That is used in the bottom of the overdrive to keep the reaction plate in the correct location. So, next, we have the underdrive shaft, which is this. This is the next pulled out. There's thrust washer glued in place. Notably looks like a turtle. Check that out. Goes back on there. And that is the underdrive input shaft. So the underdrive comes out next. There's one snap ring at the top that holds the underdrive in place. Finding where the ends were buried is the trickiest part about this one. And then getting them to unseat. So here is the underdrive snap ring. This one is a tapered snap ring. As you can see, it is tapered. That's what holds the underdrive down. Next is the pressure plate. This is the pressure plate for the underdrive. It's held in by that tapered snap ring. So next come the underdrive clutches. The first can be removed without removing the next snap ring. The next requires another snap ring to be pulled out. Okay, so here is the flat snap ring for the underdrive now that it's out. And now the rest of the clutches can come out. These are notably more worn than any of the other clutches in the transmission. They're quite worn down to their wear marks. Not terribly burnt. They probably would have shifted fine, but they would have been the failure point later in the life of this transmission. As you can see, there are 4 steels and 4 friction surfaces here. Results in a pretty strong clutch. So next you'll see in the bottom here we have the piston for the underdrive clutch. And the whole shaft of this assembly moves up and down to apply the underdrive and then the reverse. It's all reactionary of these 2 elements moving. Okay, now we're going to remove the underdrive and overdrive piston. We use a hold down tool, snap ring pliers, in this press.
I never understood that too. People say, oh, that's sick. Here's my ginger ale.
Snap ring comes off, just like that.
So pretty, oh so pretty,
And here's the piston. And there's the return spring, holds it down. And there is underneath that. Alright, so now the underdrive return spring and retainer have been removed, and the underdrive clutch piston can come out. There's a snap ring beneath that I've already removed just for ease of access. That's the input hub's tapered snap ring. This is a tapered snap ring, tapered on the inside. So now the input hub can be removed. Now this can be done one of two ways. You can either tap on it with a hammer or use air. Going down into the input. That removes that. And then the rest can easily be removed from the rest of the input hub. Okay, so in a live unit here, we would have already cleaned everything, replaced all of the seals, which are clearly here not been replaced. Bearings may have been replaced. This shaft would have been taken out. There's a copper thrust bearing in there. That should have been replaced. All of that would have been replaced. There's also seals inside of here and this fluid. We're going to use it just as an extra bit of lubricant to put it back together. So that goes back. The input shell. That lines up with the clutch. So now that all turns. Okay. So now the assembly is put back in, and the snap ring goes down to hold it down. This being a tapered snap ring has to be seated all the way. So now the snap ring is fully in place. The next piston goes down. This is the underdrive piston. It's now locked into place. And we'll go back over the press. So now we're going to install the top part of the piston. This involves a special tool, it's a seal saver. So it slides down on the shell. And then the piston itself slide all the way down like that, with the spring, of course. Once again, using the cage. So now we can put the snap ring back in. Okay, so the snap ring is now installed. We'll release the press. It holds. That's how you install that. Seal saver now comes out. That's ready for clutches. Okay, so now we're going to demonstrate all three piston applications on this input clutch assembly. First is the overdrive, where this is shoved down. And it seals quite well. Next is reverse, where the shell is forced up to engage the reverse clutches. Also seals very nice. Now this one can make a little bit of racket. It is the underdrive, which applies this lower piston up, but typically it will force the whole assembly to shoot up. You'll see what I mean. Alright, so now the underdrive spring retainer and snap ring are in place. Beneath the spring, we can put in the underdrive clutches. And this is those. Now, it's quite critical to line these up to ease the installation of the underdrive shaft. Now those are in. Okay, so now the flat snap ring will go in on top of the underdrive clutches. A little screwdriver help for this one. Okay, so So now the snap ring is fully installed. You can install the last clutch disc. Now, once again, lining up these frictions is critical. Making sure that they will all go in together when this is installed. Okay. Now that's in place. And now the reaction plate can be installed with the tapered lip side up. So now the tapered snap ring can be installed to hold the reaction plate in place. Alright, so paint side up, that's the taper up. Might need a little screwdriver help on this one also. Just kind of work your way around with that one. And there it is, buried. Okay, now the wave spring has been installed. We're going to install the overdrive and reverse reaction plate. It goes all the way down, and I will need an assistant to assist me in installing the snap ring on the outside of this one. He actually needs to hold down on the reaction plate while I put in the tapered snap ring. Just have to walk its way inside. Okay, and that's installed. Okay, so now the reverse is going to be installed. This is the final clutch and the input shell. It's installed just like that, and it has the reaction plate at the top. Just a little bit of encouragement to make that one go down. Now there's another snap ring here. This is another tapered snap ring. Okay, so now that the snap ring is all the way in and the land has been buried, the reverse clutch is fully installed. So now we can air check the reverse. That's applying the overdrive, and there's the reverse. That one's okay, good to go. So next we can put the planetary in just to see how it all fits together. Okay, there you go. Input all the way to the back where the rear gear sits. That's your input clutch.
Before you take the differential cover off, you want to take the preload out of the bearing so it doesn't crack the differential cover when you're actually taking it off. In order to do that, there's a little tooth that holds the outer adjuster for the preload. It holds it in place so it can't move. So you take this tooth off, and then you'll take your special tool and put it into the outer adjuster, and then you just go ahead and loosen it. And now there's no preload on the bearing, so you can safely take the differential cover off without cracking any of the ears or any of the aluminum case on it. So in order to adjust the bearing preload on this, what we have to do is turn the torque wrench until it's at 19 to 20 inch-pounds of torque. And in order to adjust it, you take this spline and you tighten this outer adjuster. And you mark down the torque when the torque wrench over there gets to 19 to 20 inch-pounds. So I'll demonstrate that now. As he's turning it, you'll see me tightening this until he tells me to stop. And that means that we got the correct turning torque.
About 14, only a little bit more. Stop.
So I got about 60 foot-pounds on this torque wrench, and that gets us the correct turning torque on that torque wrench.
Just about 14 right now. The next step is pinion depth measurement. This involves removing the bearing from the pinion shaft and the transfer shaft to correct the pinion shim. This will allow us to measure the height of the pinion shim and also set it to the correct height on the ring gear, as the pinion will be riding directly on the ring gear. The pinion bearing will need to be removed first, as it's used in the measurement procedure, as you'll see now. Next, we have to zero the dial indicator that we'll be using to measure the pinion depth. To do this, we use special tool 65496, which involves an end on the dial indicator and a specially designed tool. Okay, so now the gauge disc is installed into the front transfer shaft location with the shaft bearing. The centering nut has been installed at the top. The swing gauge has been installed into the side of the case, as you'll see here shortly. And what we're looking at is the pivotal swing when the dial indicator is turned. We have to kind of hold it center in order to get an accurate measurement. And we're looking at the two bottom numbers. It will bottom out at a certain number, and that's what we will calculate our adjustment factor. So here you can see setting up the gauge into the adjustment hole, and it's swinging back and forth, bottoming out at 33 thousandths. So that's what our shim thickness should be. That's what ours needed to be adjusted to put this back together.
So once you find the correct pinion shim size, you're going to have to put the pinion back into the case. Once the bearings press back onto the pinion, we'll push it up into the case and then put on the special holding tool. What this holding tool will do is keep it steady and hold it so that the bearing can be pressed onto the top of the shafts using this tool. And then you just use an arbor press and press the rest of the bearing onto the shaft.
And here you can see the output shaft spinning with the pinion. The gears have been installed and the transfer shaft is all connected. The final two topics include the hydraulic schematics and the electronic controls of the 42LE transmission. Park, neutral, reverse, first gear, second gear, third or direct drive and overdrive will be covered in this next topic. First up is park and neutral, which involves the manual valve being placed in the park or neutral positions. This turns on the 2-4 and low reverse solenoids, which blocks flow and forces the solenoid switch valve to move over, so that when the low reverse and converter clutch solenoid is energized, the low reverse clutch will be filled along with line pressure fluid from the manual valve being forced directly into the clutch. The low reverse switch is moved over, which allows this low reverse clutch to be filled. The line pressure switch is also turned on directly after the solenoid switching valve, which updates the PCM and allows it to know that fluid has made it past the solenoid switching valve. What this does in the grand scheme is allows for a firm driveway shift into first or reverse depending on where the manual valve goes. It is important to note that all other clutches are currently venting, as the vehicle may have recently been driven or perhaps just started. Fluid is directed into the torque converter and through the cooler to ensure that the fluid going in is close to the operating temperature that it should be at. It is also important to note the position of the regulator based on its Z, Y, and W valves. W valve is the only one currently being acted upon, and therefore line pressure stays at a maximum of 120 to 145 pounds per square inch at this time. This allows for a firm shift into first or reverse to avoid slipping clutches and causing premature failure in this transmission. Next we move on to the neutral shift, which is very similar to park and neutral, except the low reverse and converter clutch solenoids are not energized, and therefore the low reverse clutch is not being pre-filled and nothing is going on beyond the solenoid switch valve. Being as neutral is not a typically selected gear, it would not have any other purpose other than for rolling the vehicle and making sure that no clutches are applied as to not damage any parts of the transmission if the vehicle were to be towed or pushed. Next comes reverse, when the shift lever is moved into the reversed position from either park or drive. It is important to note fluid pressure from the manual valve is now acting on the Y port of the pressure regulator, raising line pressure to approximately 175 to 235 pounds per square inch, notably higher than any of the other gears in this transmission. This is used to make a very strong apply going into the reverse gear to avoid clutch slippage and also allow for a very firm driveway shift to avoid damaging the transmission. You may also note that none of the solenoids are energized during a reverse shift. This is to allow for the transmission to go into reverse no matter what has happened to it. If an electronic failure, if it's lost power, maybe the PCM went down, but the vehicle's still working, you'll always have reverse gear, and this works the same way with another gear that will be explained later. Since the 2.4 and low reverse solenoid is not energized, fluid is allowed to flow through it to the manual valve, which then sends pressure to the Y port and the low reverse clutch through the low reverse switch. Also, fluid from the pump is sent through the manual valve to the reverse clutch through its number 4 check ball and orifice. The bleed port in this case is closed off and does not allow full pressure to go into the cooler and the torque converter. So less than line pressure is going down to the torque converter and into the cooler at this point. One of the fail-safes built into this transmission is for the vehicle to block out reverse gear if it is selected at the wrong time or maybe at a higher speed than it should be. An example is above 8 miles an hour, the 2.4 and low reverse solenoid will be energized, forcing fluid to stop flowing to the manual valve and to the 2.4 clutch pack, and force it into the solenoid valve to be vented back to the pan. This keeps the transmission from going into reverse at a speed greater than 8 miles an hour, which would effectively damage the clutches and possibly just cause them to slip or do nothing in this case. Going back to park and neutral, you'll see that low reverse was pre-filled because of the application of the low reverse and the 2.4 low reverse solenoids, and you'll see how this plays into first gear as it will be selected next. Now the shift lever has been moved into the drive position from park or neutral. So the low reverse and 2.4 low reverse solenoids are both energized. The low reverse clutch pack is completely filled. It was pre-filled from park and neutral, and now fluid is flowing through the manual valve up to the underdrive and overdrive solenoid check balls, which are both being blocked off because both of those are off, and fluid is flowing directly into the underdrive clutch pack. This enables first gear, which has a ratio of 2.84 to 1, so every 284 times the crankshaft is turning the torque converter, the output shaft turns 100 times. To make the shift to second gear asynchronous, the low reverse and 2.4 solenoids are both turned off, which fills the 2.4 clutch pack through the manual valve by the 2.4 now flowing fluid directly into the line pressure on this shift is around 120 to 145 psi, very similar to first gear, as the W port is still being acted upon, which allows the regulator to stay in place. The manual valve is also allowing fluid to go to the converter clutch switch, which in this case is still closed. Fluid is flowing through the torque converter normally and also through the cooler through the converter clutch switch and venting back to the pan after it gets through there. Second gear, like reverse, operates with no solenoids energized and uses only the manual valve to dictate which clutch packs are applied. That allows this to be the fail-safe gear in case electronics were lost, and it's also the limp hint home just in case everything failed on the transmission other than the clutch packs and line pressures. The second gear has a ratio of 1.57 to 1, so every 157 turns of the crankshaft translates into 100 turns of the output shaft of this transmission. So at this point the transmission has already made the shift into second gear. It's been driving along and it has decided that it is time to apply the torque converter. Now this may have turned on because the transmission is going down a hill, or maybe the manual valve has been selected to the 2 position or the low position in this case. This would ultimately allow the low reverse and converter clutch solenoid to be modulated now to allow some pressure through to turn on the converter clutch switch, which would then allow certain amounts of fluid pressure to act on the torque converter clutch and apply it to a certain degree. Next is the shift into third gear, which is also called direct in this transmission, since it is a 1-to-1 ratio. So every time the crankshaft spins, so does the output shaft when direct gear is applied. This is an asynchronous shift from second gear, as the underdrive is remaining applied, and the only element that is then turned on is the overdrive, which is done by turning on the 2/4 and low reverse solenoids. And also the overdrive solenoid will be turned on to allow fluid to pass the check ball on the overdrive solenoid and fill the overdrive clutch. Fluid pressure from the overdrive clutch is now being pushed into the Z valve of the pressure regulator, dropping line pressure down between 75 and 95 psi. With pressure acting on the Z port, the regulator also uncovers a tap that goes to the torque converter regulator switch, which sends fluid from its T port to the converter clutch switch, which allows the converter clutch switch to direct pressure directly into the back of the torque converter's clutch and effectively turning it off during the direct gear application. This protects the torque converter's clutch, especially while the shift is happening. For a later date, the torque converter clutch can then be turned on. At this point, the switch to the direct gear has already been made. The clutches are firmly applied. Line pressure may drop off slightly at this point as the demand from the pump is less, as it's only holding the 2 clutches in place. Now the converter clutch switch is slid over. Pressure is being manipulated by the low reverse and converter clutch solenoid from the switch valve at this point. So pressure is now building on the torque converter's clutch side of the torque converter, which is allowing it to apply fully in third gear. Now this may happen because a lower gear has been selected with the shifter, or also in the instance that the vehicle is overheating. If it is in an overheat strategy, then the cooler will also be used to its complete maximum, and the direct gear will enable the torque converter to stay on completely, even into a second gear shift then, in efforts to hopefully cool down the transmission by not using the torque converter as much. The next shift is to fourth gear, or overdrive. It's called overdrive since it is a 0.69 to 1 ratio. It has then 69 turns of the engine will result in 100 turns of the output shaft. This shift is also asynchronous since one clutch is unapplied and another is applied. The overdrive is the only one that remains, so the overdrive solenoid remains on, and in this case the underdrive is turned on. When the underdrive is turned on, fluid is now blocked going to the underdrive clutch pack, and the 2/4 becomes turned off, so fluid is then allowed to flow through the manual valve to the 2/4 clutch pack. This effectively enables fourth gear. Just a couple things to note about fourth gear in this transmission. The fluid that is being vented off of the multiple different clutch packs in this case, and out of the torque converter, all will travel through the converter clutch switch and into the transmission's cooler. Now the bypass is no longer active as the pressure is not high enough to push it through, so all the fluid will travel through the cooler at this point and return back to the pan. Now line pressure in this case, since fluid is being acted still on the Z port from the overdrive clutch, this results in a line pressure of 75 to 95 psi, very similar to the third gear clutch. At this point, the transmission has safely shifted into fourth gear, and the low reverse converter clutch solenoid is being modulated by the ECM to turn on the torque converter clutch by varying pressure to the converter clutch switch, which allows more or less pressure going to the torque converter's clutch, turning it on at this point and partially locking it up. Now the converter clutch solenoid is fully on all the time. It's no longer being modulated. What this does is turns on the torque converter's clutch 100%, locks it all the way up, and creates the largest amount of reduction. There's no longer any magnification in the torque converter, and this is going to be used for cruising speeds on the highway and also while going down hills. This setting would typically be turned off if the vehicle encountered a hill or a heavy load instance.